In this video, we'll go into how you know what substitution to make when you're trying to solve an integral by trigonometric substitution. So we have several options here for what we could pick for our functions to put in for our trig sub method. How do we know which one to use? Well, the way you know what to use is what does the expression look like inside of your square root or complicated expression? And the thing you want to take advantage of here is how do our trigonometric functions behave based on the Pythagorean identities? So the basic idea is, since we know that 1 minus sine squared theta is cosine squared theta, or more generally, a squared minus a squared sine squared theta equals a squared cosine squared theta, what this tells me is if I see square root a squared minus x squared, I should plug in x equals a sine of theta. Why? Because if I do that, I will then see this thing under the square root, which simplifies to an a squared cosine squared theta, and then the square roots go away with the squareds. So we're taking advantage of the structure of how these trigonometric functions relate to each other to tell us what to plug into those expressions. So if I see a squared minus x squared, I should plug in a sine theta. Similarly, since 1 plus tan squared theta equals secant squared theta, then if I see square root of a squared plus x squared, then I should plug in x equals a tangent of theta, because then I'll see a squared plus a squared tan squared theta, where I can then use this, convert that to a secant squared, and then the square root goes away. The idea is always get rid of the square root. That's really where you want to head with all these problems, get rid of the square root and see where that goes. And for the final one, since we know that secant squared of theta minus 1 equals tan squared theta, if we see root x squared minus a squared, so the opposite of the sine one, I want to plug in x equals a secant theta by the exact same logic. Plug that in, things cancel out, I get down to a perfect square under the square root, and the square roots go away. Always going to get rid of the square roots. So these are your three main indicators of when you're going to want to apply trigonometric substitution. It's going to be when you see something like a squared minus x squared, a squared plus x squared, or x squared minus a squared under a square root to some weird power. Anything like that is a good indicator of when you should try trig sub to solve out these problems. So here's an example here we're going to try. Compute integral of dy over y squared, square root of y squared minus 5. So this here looks fairly complicated, but the key thing to spot here is the y squared minus 5. If you look back to our previous page of notes, seeing y squared minus a squared tells me that this should be a secant substitution. So I want to set y equal to root 5 secant of theta. So then dy is root 5 secant theta tangent theta d theta. Now let's just plug all this in. So I get the integral of dy, which is root 5 secant theta tangent theta d theta, over y squared, 5 secant squared theta, square root of 5 secant squared theta minus 5. This part under the square root is a 5 tangent squared theta. This 5 will cancel with this root 5, and I'll be left with a tangent on the bottom. This will give me the 1/5 from the 5 sitting out front, integral of secant theta tangent theta d theta over secant squared theta tangent theta. The tangent thetas cancel, the secants cancel with one of these, and now I have a 1 over secant, which is a cosine. Well, that's easy to integrate. That's just sine. But now I have to figure out sine theta in terms of x. So our trig sub before was y equals root 5 secant theta, which means my triangle should look like this. I have my triangle, I have theta. Secant theta is y over root 5, which means I need y over root 5 to be that, because secant is hypotenuse over adjacent. So then this here should be y squared minus 5. And then I get my answer by just plugging this in. I get 1/5 sine is opposite over hypotenuse, root y squared minus 5 over y plus c. And that's how you get this problem here by trig substitution. So again, the steps of the process, figure out the substitution you want to use, and that depends on looking at your formula and seeing which of those expressions do you have. Do you have x squared plus a squared? Do you have x squared minus a squared? Do you have a squared minus x squared? See which one you have, use that to tell you which trig sub to use, plug it in, see what happens, and see if you can solve the integral afterwards. That'll give you the idea of how you set up pretty much all of these problems by trig sub and how you know which substitution you should pick in order to accurately solve the problem and get to the answer without going in circles about it.